So the last presentation today is coming from Yaxiong, and it's called Partially Observable Reinforced Learning for Dialog-based Interactive Recommendation.
Hi, thank you. Thank you for your introduction. Hello, everyone. My name is Yaxiong. I'm very glad to be here to present our work, Partially Observable Reinforcement Learning for Dialog-based Interactive Recommendation. This is a joint work with Macdonald and Iadh Ounis from University of Glasgow. So, in the dialog-based interactive recommendations, natural language feedback allows recommender system to obtain rich information relating to the user's current preferences. Here we show an example in the action sequence for a recent reinforcement learning-based model. So in this example, a user keeps a target item in mind. The recommender system makes a random initial recommendation first, and then update the recommendations according to the user's feedback, according to the, so one step by step. During this multi-turn interaction process, we observe, some recommendations that violate users' previous feedback. For instance, the single red color is violated by the initial comment, blue slides on clocks. We also observe repeated recommendations. These are caused by the fact that, So these are caused by the fact that the natural language feedback can only provide a partial portrayal of the user's preferences at each turn. Such partial observations issue make it challenging to track users' real preferences over time correctly in such a partially observable environment. So reinforcement learning has been adopted to formulate the interactive recommendation tasks by dealing with how the recommender agents ought to make recommendations during the interactions with users, considering their preferences in order to maximize the cumulative rewards. For instance, a supervised Q-learning network has demonstrated a general better performance in sequential recommendations by introducing reward-driven properties to the recommendation process with a Q-learning layer. Furthermore, when complete information about the environment is not available, a reinforcement learning problem is modeled as a partially observable Markov decision process. However, the existing reinforcement learning-based models formulate the dialog-based interactive recommendation task as a Markov decision process while ignoring such a partial observations issue. So we consider that the Q-learning for POMDP can be suitable for addressing the partial observations issue in the user's natural language feedback. To this end, we propose a novel dialog-based interactive recommendation model called the Estimator-Generator-Evaluator model. So it's EGE model, which formulates the dialog-based interactive recommendation task as a partially observable Markov decision process to address the partial observations issue in the user's feedback. And we extend the SQN framework from MDP to POMDP and judge the quality of the estimated user's preferences with a Q-learning layer. So compared to the SOTA models from the literature, we adopt reinforcement learning with POMDP to mitigate the violation and the repetition issues with the natural language feedback only. And we take IGRU and MBPI as baseline models in our experiments. The RCR model is not compiled because it requires extra well-categorized attribute information. So this figure shows our proposed end-to-end EGE model. Specifically, we leverage an estimator to track and estimate the user's preferences, a generator to match the estimated preferences with the candidate items to rank the next recommendations and filter out the repeated recommendations. And then an evaluator, a Q-learning layer, to judge the quality of the estimated preferences considering the user's historical feedback. So in this work, we adopt a multitask learning approach for POMDP to optimize the networks with a combination of supervisor learning classification laws with cross-entropy and Q-learning prediction laws with one-step temporal difference error. So we jointly train the supervised laws and the reinforcement learning laws by taking the latter one as a regularizer to introduce reward-driven properties to the recommendation process. In our experiments, we address 3 research questions that relate to how useful the Q-learning for POMDP is, whether the historical information is required, and how the rewards are applied. The third research question is about the ablation study. More details and the results can be seen in the paper. So here we mainly introduce about the first and second research question. So in our experiments, we perform experiments on 2 data sets, namely the shoes dataset and the fashion IQ dress dataset. Following common practice, training and evaluation use a user simulator. So given a target image, the user simulator is trained to provide textual feedback on each candidate image. For the success, the success is measured by getting the target image in less terms and ranking it more highly at given terms. We also experiment with filtering out repeated recommendations. These figures show the recommendation effectiveness of the tested models for top 1 recommendation in terms of NDCG at 5, while varying the number of interaction terms on the shoes and the fashion IQ dress datasets respectively. The solid and the dashed lines show the model's performances without or with a post filter respectively. Comparing the results in the figures, we observe that our proposed EGE model generally achieves a better overall performance at various interaction terms without or with a post filter respectively, but except for the initial term. And the other metrics such as NDCG at 10, MRR at 10, and success rate at also show the same trend, but limited by time here, we don't show here. And to quantify the improvements, we measured their performances at the 10th interaction term. So in this table 1 shows their performances at the 10th interaction term. It contains 2 groups of rows for each data set without or with a post filter. We observe that the EGE model achieves significant better performances without or with a post filter on both data sets. So therefore, in answer to the first research question, our proposed EGE model with Q-learning for POMDP can effectively mitigate the partial observations issue. And in response to the second research question, according to the results in the figures and the tables, we can observe that our proposed EGE model can benefit from both the user's historical feedback using a Q-learning layer and the agent's historical recommendations with a post filter. To consolidate the results observed in the previous slides, we present a use case of the tested model without or with a post filter. For a fair comparison, the initial images are the same across the tested models, given the same target image for the testing set. We observe that our proposed EGE model is the most effective recommender system among the tested models. Both EGE and EG filter only needs 2 interaction turns to display the desired item, while the other tested models require at least 4 interactions given the same target and initial items. So in conclusion, our proposed EG model with Q-learning for POMDP can effectively incorporate the user's preferences over time in a partially observable environment. It achieves significantly enhanced performance compared to the strongest baseline model, and it can benefit from the historical information. For the future work, we plan to investigate an end-to-end model with historical recommendation features into the preferences estimation process. And we also plan to try to generate better fashion image embeddings by denoising the features from the human models. So thank you, everyone. If you are interested in our work, you can find more details and results in our paper. Thanks.
So, thank you very much for your presentation. So, would you mind to summarize quickly the results of your ablation study?
Summarize?
Yeah, just shortly describe how you did it.
Okay, so I think I cannot go back to the slides. In the user study, in the use case, we showed the results with different models like IGRU, MBPI, and our EG models. We consider to adopt a post filter, or we don't use a post filter. So we compile the results in 2 columns. And we find that if we adopt our EG and the EG model without a post filter, we only need 2 interaction turns in addition to the initial turn to display the desired item. But if we use the other baseline models such as IGRU and MBPI models, which don't consider the partial observations issue, they need at least 4 interaction turns, and given the same target and the initial items. Yeah.
Okay, thank you very much. So we have another question from Taoye. She's asking, could you give an example of a full dialogue between user and the system? Does every turn present a new item recommended for the user with some description? What's an example of a partially observed user input?
Yeah, so as I have demonstrated in the second slide, I demonstrate an example generated by a model, reinforcement learning based model. So there is a complete, a full dialogue between user and the system. So the user keeps a target image in mind and then give comments according to the recommender system's recommendations. So step by step, this conversation process forms a full dialogue between the user and the system. The user tries to describe the difference between the user's target item and the candidate recommendations. So that's the full dialogue example. Yeah. So at each turn, the recommender system tries to present an item according to the algorithm. So it can be a new item or old item according to the scores generated by the model. And what's the example of partial observable user input? So I have described that in my example. For example, the user keeps an target item in mind. It can contains a lot of features, like an image. We cannot describe with a single sentences. We cannot describe all the features in a single sentences. So in each turn, the user can only describe one or two or several features at each turn. So but the system cannot observe the user's real preferences. So it's a kind of partially observable environment. So that's the partially observable situation or environment. Yeah.
Okay, thank you very much. So we have another question. Maybe if you can answer it quickly, we can do it. Which model do you use to extract features from images? Do you use data augmentation or transfer learning?
Okay, so in our model, we use the pre-trained reciprocal net to extract features from images. Actually, we use a user simulator to generate enough data. So you can consider it as a data augmentation, but it's a little different from the data augmentation. And yeah, so I think that's a question. Yeah, and yeah, I think what do you mean by data augmentation, transfer learning? Here, maybe we need to transfer the images into different types of the images. Also, I think the RecSys has considered these things. Yeah.
Okay, thank you very much. So that's it, I guess. And we actually invite authors and the audience to interact with each other on the hub. And that's all for this session. Thank you very much for staying this late.